Yes, thank you for the introduction. I'm Maciej. I currently hunt fraudsters at Ravelin in London, but for most of my computer science career, I've been building recommender systems. So today I was hoping to walk through a couple of things in which recommender systems aren't like any other application of machine learning that you could have in production. And so if you expect your recommender system to behave like any other application of ML, you may be disappointed. Part of my claim to fame is I'm author of LightFM, which is a popular Python recommender system package. And I worked at List, which is a fashion e-commerce company based in London, and I worked on recommendations at Netflix, which is a video streaming service you may have heard of. So my central thesis, as I said before, is yes, recommender systems are an application of machine learning in production, but they are sufficiently different from classification to require special treatment. And there are three main areas in which they are different. Firstly, it's model choice. How do you choose a model? What constitutes a good model? So in classification, for instance, it's fairly easy to find a good baseline. Any classification problem you have, a random forest is probably going to work reasonably well. Except if you have images, in which case you use a convolutional neural network, and then you'll basically be fine. This isn't the case with recommendations. So there are a number of standard approaches, which are used widely in the literature. So for instance, there's a famous class of models that won the Netflix prize called collaborative filtering models, where you use information about how people buy or use your items to recommend items. But these could be virtually useless for your application. So if you just go to the literature and say, well, Netflix and Amazon use this sort of model, it has to be good, I'm going to use it in my system, you can be in for disappointment. You need to have a careful look at your problem. So, for instance, if novelty is an important component if you're in your system, let's say you recommend news articles, a collaborative filtering approach may be completely useless to you. What is a collaborative filtering approach? Well, in a collaborative filtering approach, when you want to recommend a news item based on another news item, you basically look at, well, what sort of users looked at these two news items, right? If a given set of users looked at item A, and the same set of users looked at item B, that means these two items are similar. And if somebody looks at item A, you should probably recommend them item B. Can anybody see a problem that you might have if your business is recommending news articles? Well, news is an area where novelty is sort of important. So if you try to use collaborative filtering on new articles, well, if an article is new, nobody's probably looked at it. So you don't have any data to base your recommendations on, right? If you have two articles and nobody's looked at any of them, how do you recommend them? So this particular model would be useless in that application. The second thing you should have a look at is popularity. Like, is popularity useful in your model? Again, in user recommendations, if an article is popular, that's probably something you should use in your recommendation model. If something is popular, people are interested in it, you should use it. Another thing you should have a look at is continuation. And what do I mean by this? Well, if you're an e-commerce site and somebody went to your site before and they had a look at a couple of items, maybe they had a look at them and they bookmarked them, and when they come back, they want to see them again because they want to purchase them. For the Netflix application, well, if you started watching a TV series and you come back to Netflix, what are you going to do? Well, chances are, if the series is good, you're probably just going to continue watching. And that's why you have the continue watching row in Netflix. And if your recommender system didn't account for that use case, it wouldn't be a very good system. And the final component is metadata. So let's say, again, you have this news recommendations problem, and somebody comes to you and you know a little bit about them, what sort of things they're interested in, and you want to recommend news articles to them. And these news articles need to be new. Well, nobody's interested in something that's months and months old. But something that you can use is metadata that you have on articles. So if somebody's interested in sports, and you know a given article is about sports, even though it's new, that gives you something to go on. So that's something you can use. When in doubt, ensemble. So there are all these different types of models that you can use. if you don't know which one is the right one, or indeed, if there is a right one, ensemble them, i.e. take all these components, mix them together, and see what sticks. See which model performs better. So yeah, so that's how you select models. But how do you know a given model is better than another? And that's another area where recommender systems are different than simple classification. If you have a classification problem in your system, normally you'd take your data, you fit some models offline, you'd define a metric like accuracy, and say, well, I have these 4 models, these are the accuracy metrics, the one that's got the highest accuracy metric, we pick this one, and that's what we run with. In recommendations, there is an equivalent. These are called ranking metrics. Basically, the goal of your system is to compute a ranked list of items to recommend to a given user. So hopefully a good model will put items that the user will like at the top of the list and items that they won't like at the bottom of the list. So the way you would do it in offline testing is you take your interaction data, you hold out some interactions into a testing set, fit your model in the training set, and then check that the interactions you held out are at the top of the ranked list given your model. And that's what the ranking metrics give you, and there are a couple of them. But even though you do have these metrics and you have to use them, evaluation is still difficult. The first question is, what do you even measure in the first place? So imagine again you have an e-commerce site, and there are 3 types of actions your user can perform. They can browse, they can click on items, right? A click is an expression of interest. If they click on an item, maybe they'd like to buy it. They can also favorite items or save for later. So there's a special button which stars an item or adds it to bag, and that's again an expression of interest. And the final expression of interest, and arguably the one that you're interested in, is a purchase. And so in this case, like what do you measure when you fit your model, when you evaluate your model? Do you care about the clicks, or do you care about the saves or the favorites, or do you care about the purchases? Well, let's say you care about the clicks and you fit your models and you look at how well they perform in predicting clicks. But that could actually be terrible for your system because people click on anything and everything, and that might not be correlated with what you want, which is, will they buy stuff? So then you move on from clicks to favorites. This is a stronger signal, right? They save something for later. But then again, like if you're in e-commerce, people save lots of stuff, and if you're in fashion, people might save stuff that they really love, but which costs thousands of dollars and they will never buy. It's more like an aspiration, like if I were rich, this is what I would buy, and they save it. So if your goal again is predicting purchases, this isn't going to be very useful. So in the final iteration of your system, you move on to what people actually buy, right? So we take our data on what people buy, and we hold out some purchases, and then we try to rank all the items such that the purchases that we held out are at the top. But it turns out that the model you get out of it is virtually useless again. It doesn't give you any useful information because purchasing data is sparse. Like any user that you have hasn't probably purchased lots and lots of items. They maybe buy 2 or 3 or 4 items, and that isn't enough to train a model. So any of these on their own aren't good evaluation metrics. They aren't good training data. So we need to think about the metrics that you care about and how to combine them and how to use them for training. So there isn't, unlike in classification where you just look at the accuracy, there isn't a straightforward choice here. So you need to, even when evaluating your models, you need to be really, really careful about what you're measuring, and if what you're measuring is really what you care about. The second problem, which is quite big in recommender systems, is the future like the past? And that's sort of true for classification as well. You may think that, well, you have some training data and you train model on the training data, but from tomorrow on, the data that you get for classification is going to be completely different. And that could happen, but it does happen all the time with recommendations. So as an example, let's say we have a new collection. I worked in fashion. We have a new collection of dresses, and these dresses are going to be immensely popular soon after they're released. And if you train your model on that data, it's going to predict that that people will buy these dresses. But this is a new collection, and in a couple of weeks' time, people are going to forget about it. And so the future isn't like the past. People's tastes change. The things that are popular change. So you need to take account of that. And the final problem, which is peculiar to recommender systems is presentation bias. So imagine you have a system where everything is recommended. Everything that the user sees is the result of your system. If you take the interactions that this system produces and train another model on it, what is that other model going to predict? The only thing it's going to predict is what your previous model predicted. Because the only information you gather from your system is influenced by what your current system is doing. So if, and the extreme case of this is services that, let's say, send you a box of things, and you have no choice in what these things are, and then you can just keep or return some of those items that you get. The only way that the user interacts with that system is what they keep, but the only thing that they can keep or not keep is what the system sends to them. So there is very little outside information that can get your system out of a local minimum, and that's a big problem. And there are a couple of ways of dealing with it. One way is, well, you give your users some random recommendations, and then use that piece of random data as an unbiased evaluation set. Another way is you can record what your system shows to people and say, well, if this item we showed to people lots and lots of times, the fact that they didn't buy it or didn't like it is a much stronger signal than if we didn't show that item. So there are a couple of approaches to do this, and they're quite useful but don't quite solve the problem. And then the final way is, when you design your system, you should design some escape hatches into it. So not everything that the user sees is a result of your recommendations. There has to be a way for them to go around your system and give you some independent information. And then that information can allow you to bootstrap your system out of the local minimum it might be in. And the final way in which recommender systems are different is the engineering architecture. So the classification paradigm is you train and evaluate model offline, and then once you have the model, you spin up a service that accepts features and returns a prediction. So anytime your system wants a prediction on a given item, it goes out to the database, it fetches some features, it serializes these features into a blob of JSON, sends it to your service accepts this, makes a prediction, returns the score or classification. If you try to do this with a recommender system, you are going to have a very bad time. And the reason for this is you're going to be scoring lots and lots and lots of items in the recommender systems. It's not just one item at a time. It's tens of thousands or hundreds of thousands. And so ranking is computationally intensive. Let's say you have an e-commerce site or something like Pinterest where they have millions or tens of millions or hundreds of millions of items, and you want to recommend the most relevant or interesting pins. What you need to do is you need to score lots and lots of things. So you need to generate candidates from millions of possibilities and score tens of thousands of candidates. So imagine this. In a lot of these systems, the way you represent these items is through these high dimensional vectors. So basically lists of numbers. So if your single item is, let's say, 256 floats, that's a kilobyte on its own. And then if you want to score 1,000 of them, that's a megabyte. And if you want to, but you're probably going to be scoring tens of thousands, hundreds of thousands. So if you had this, if you designed your architecture like any other classification system, where you go out to the database, get the data, and then serialize it, send it over the wire and wait for the prediction, the serialization overhead and sending things over the wire would take so long, users will get bored. So you can never do that. So yeah, ranking is extremely computationally intensive. And the way you get around this is, there are a couple of ways. One, your model has to be local to your data. Like, it just has to live on the same box where your data is because of the serialization overhead. So when you design your system, you need to take that into account. Your model and your data have to live in the same place. The second way is, well, can we save us some of the work? Like, do we need to compute all of these? Do we need to rank all of these millions of candidates? Maybe you don't. And then you have heuristics, like, well, these items are older than 3 months, or maybe they're less popular than some threshold, and you don't score those because they're just bad items. Or maybe use some sort of clever space partitioning technique where you have these latent representations, and then you can carefully slice this space into subsets where you know that similar items live, and then when you want to retrieve related products, you just go to that subspace and not have to scan the whole thing. So there are clever ways of getting around this. One other way is pre-computing. So instead of doing this as the user is waiting, you have a system that goes through your data and computes the predictions and scores them in some sort of cache or database. But pre-compute can't always help you, because a lot of the prediction has to happen online. As a simple example, imagine you have a new user and they don't have any history of interaction with your site, and you still want to make predictions for them. So one way of doing this is you accumulate, as they interact with your system, you accumulate pieces of information. So they land on your homepage, and then they click on product A, and then product B, and then product C. And if you're designing a smart system, that system will take these pieces of information into account and will fold those into a model of that user. So you can start serving the predictions as soon as that user arrives, without having to wait for the pre-compute cycle. That's, by the way, how YouTube does it. As you explore YouTube and you click on videos, they immediately update the model that they have of you and generate relevant recommendations. And that you can't pre-cache it. That has to be online. Yes. So pre-compute can help you. Another way in which pre-compute can't help you is, even if you have a model of a given user, the particular context that they're in can be relevant for recommendations. So again, in the context of YouTube, or maybe in the context of Netflix, like maybe in the morning you want to watch different stuff than you want to watch in the evening. And so, or maybe if you're on an iPad, you want to watch something else than you would on a desktop. So you need to take these things into account, to make a good model. And in this case, you can't pre-compute. You have to do it online. And that means that not only your prediction system has to be online, but also your fitting system. So often what you have is the prediction system has to be online, and the fitting system is always there in the background, churning and ingesting new information and updating the representations that you have. So that has certain architectural constraints as well. And it means that you don't just fit a model and then put that model into production and will continue doing what you think it's going to be doing. It's changing all the time. It's ingesting new information. So we need to have monitoring, and you need to have tools to figure out what's happening and how the model is changing. So I guess practical advice, if you're building your own recommender system. Whoops. There we are. You need to understand your application. Like, is novelty important? Is popularity important? How much data do you have? Like, if you have lots of data, maybe a collaborative system will work. If you don't have lots of data, maybe you need to use a hybrid system or use the metadata that you have on items and users to make your system work. Start small. Try popularity first. Popularity is an excellent way of ranking things. Like, if something is popular, people like it. Of course, with the caveat that if novelty is also important, you have this trade-off that something that is popular can be very old. So if you use Hacker News, and if they only rank by popularity, that would be a terrible, terrible website, because the only things you would see are items from years and years ago that were very popular. Equally, if the only thing that they used was novelty, it would also be a terrible website, because there's a lot of stuff that goes on there, and most of it isn't very interesting. Whoops again. And finally, you don't need distributed training. So if somebody tries to sell you Hadoop or Spark, they're not your friend. In a lot of these applications, especially in recommender systems, the thing that was popular initially was Mahout, and now there are some implementations in Spark. And so people say, well, if you're building a recommender model, go and get one of these things. Chances are you don't actually need them, because you don't have enough data, or maybe there isn't that much benefit of using the additional data. And so jumping straight to a distributed system is just going to give you technical cost and maintenance cost, which isn't worth it. And that's really it. So thank you, and I'm happy to take any questions.